Okay, so as I said, why we need to find or design an algorithm that has a smaller time complexity. And if there are two algorithms, we should be able to analyze the time complexity and pick the one that will take less time theoretically, and that's the one we're going to implement it. Okay, so let us use this example here, the problem of finding a prime, whether given integer is prime or not. And you should know what is a prime integer, right? So a prime integer is something where it is only divisible by itself or 1. So if you are given say 11, 11 is divisible by 1 and by itself 11. No other integer from 2 to 10 will divide 11. So what I mean by divide 11, when you divide anything by 11 other than 1 and 11, the remainder will not be 0. For example, 11 divided by 2, the remainder is 1. 11 divided by 3, the remainder is 2. 11 divided by 10, the remainder is 1. So if in general, if you have an integer n, anything other than, if you divide n by anything other than 1 or n, the remainder will not be 0. Okay, so that's the, see, as I explained the logic by in word, we can now write it in a pseudo code. So given an n, run a loop, because you know any integer n is divisible by 1 and itself. So that's why I'm running the loop from 2 to n minus 1. There's no need to check whether n is divisible by 1 or n is divisible by n. That's redundant, and we can save some time by avoiding things like that. So run the loop with index I equals 2 to n minus 1 and see if n is divisible by any of those values from 2 to n minus 1, and that's what I'm checking here. If n mod I, so mod is like the give the reminder of the division. So n mod I will give the reminder, and if the reminder is 0, then it means n is not prime. So for example, if your n is say 12, then if you divide 12 divided by 2, the remainder is 0. You can stop right there and say n is not prime. There's no need to divide by every integer from 2 to n minus 1. So in the case of 12, once you find 12 divided by 2, the remainder is 0, you don't need to divide 12 by 3, 12 divided by 4, 12 divided by 5, all the way to 12 divided by 11. No, there's no need, because just one factor, in this case say 2, is there. So n is divisible by something other than 1 and itself, then you can say n is not prime. So like in this case of 11, 11 divided by 2 is not 0, then you continue the rest of the loop. 11 divided by 3, check if it's 0. 11 divided by 4, 0, no, 0 or not. Keep continuing until 10, n minus 1. So only if the integer is indeed prime, you need to run the entire loop. So you should get the logic for analyzing the time complexity now. So if n is not prime, you would prematurely end the loop, okay, and exit the program. Only if n is indeed prime, you need to run the loop for all values of I, and then you see in the case of the integer being prime, you will not really go inside this if statement, because for no value of I, n mod I will be 0. So you will be just checking that, but you will not go into the if statement, if block. So you'll come out of the loop and return n is prime. So that's the only place you will stop the program if n is not prime. So if n is prime. If n is not prime, you will stop the program for some value of I for which n mod I will be 0. Okay, like in this case of 12 or even 15. For 15, 15 mod 2 is not 0. So we'll continue to the next value of I, 3. 15 mod 3 is 0. So we'll stop there and say 15 is not prime. Okay. Right. So now when you want to analyze the time complexity of this, again there's a looping going on, and inside the loop we do a division. So you see here you have two things that you do a division as well as a comparison. So this is where you should be able to design from a digital logic background which operation is more time consuming. Division is more time consuming than comparison. Okay, so that's why you should choose division as the basic operation. So now how many times we do the basic operation? Now you see here, as we just went through the logic, it's not the same number of times we do the basic operation for all n, right? So it depends on what is the n value. If n is prime, you will do more divisions because you have to go through the entire loop. If n is not prime, you probably don't do all the required number of divisions, right? So we'll have a best case different from worst case. So that's something first you fix, whether this is the same number of times we do the basic operation or different number of times. So in this case, yes, it's different. So what's the best case? So the best case is if you do one division, and that will happen if your n is actually an even integer. So for example, n even means like 2, 4, 6, 8, all are even, right? So any even integer is divisible by 2, right? So since you're starting the loop from I equals 2, you will find that the integer, whatever the integer is, mod 2 is going to be 0. So we will do one division and decide that integer is not prime. So for all even integers, you will do one division. That's the best case. Now, if your integer is indeed prime, then you have to do all these divisions from I equals 2 to n minus 1, right? And that's the worst case. So the number of divisions you will be doing at the worst case is the number of integers in this range from 2 to n minus 1. And mathematically you're finding it is, say, if this is the lower limit 2 and upper limit is n minus 1, the number of integers inclusive from 2 to n minus 1 is going to be n minus 1, the upper limit, minus the lower limit plus 1. So for example, if n is 11, how many integers are there from 2 to 11? And if n is 11, n minus 1 is 10. So how many integers are there from 2 to 10? It's like 2, 3, 4, 5, 6, 7, 8, 9, 10. You have to count it. So instead of counting it, mathematical formula is going to be the upper limit 10 minus 2 plus 1. So 10 minus 2 is 8 plus 1, 9. So there are 9 integers from 2 to 10, including 2 and 10. So if you simplify this, n minus 1 minus 2 plus 1 is going to be like negative 1, 1 cancels, so it's n minus 2. So n minus 2 divisions. So in general, if for larger n, as n gets larger, that's what we're going to focus, called asymptotic time complexity as we proceed in this module. So as n gets larger, n minus 2 is approximately equal to n. So we can say we'll do n divisions at the worst case, whereas in the best case we'll do one division. Okay. So any questions so far? Yeah. So I have I hide it now. Okay. Alright, so this is kind of like a naive approach just based on the definition of what's a prime integer, right? So a prime integer by definition is something that is only divisible by itself and 1. So anything in the range from 2 to n minus 1 should not be able to divide that integer. Okay, that is for a prime integer. Now, and we notice that at the worst case we will require n divisions, right? So is there something we can do better than n? And that's where we have a second approach algorithm, and you might have studied also this in a math class, but if you have not studied this yet, this is something good to know now. Now to check whether integer n is prime or not, you don't really have to divide it by everything from 2 to n minus 1. That's an interesting math property. If you explore only up to 2 to square root of n, and if anything in this range can divide n and the remainder is 0, n is not prime. And if nothing in this range from 2 to square root of n can divide n and the remainder is not 0, then we can say 100% sure that n is prime. So that's a math property. So you don't have to really go from 2 to n minus 1, just check from 2 to square root of n. and if anything in this range cannot divide n, then n is indeed prime. So with this logic, I'm reducing my range, right? From instead of 2 to n minus 1, we are going to go only from 2 to square root of n. So the best case is still one division. That's for even integers. We have to do at least one division, right? Now the worst case is where things are different. So previously we used this upper limit minus lower limit plus 1 formula. We can still use that here. The upper limit now is what? Square root of n. That's the max upper limit minus the lower limit 2 plus 1. So this is the number of divisions we are doing. Square root of n minus 2 plus 1, which is square root of n minus 1 divisions. Now as you go for larger n, square root of n minus 1 is approximately same as square root of n. But you should now realize square root of n is not same as n. Okay, so as you have different values of the input size or the integer n, the first algorithm will take same number of divisions. So if n is 10, you will require 10 divisions. Of course, it's n minus 2, but as I said, as you increase n, n minus 2 is almost same as n approximately. So if n is, say, this is what, 10 million, the number of divisions you do is also 10 million. Whereas the second algorithm, the worst case is square root of n. So in square root of n, if it's 10 million, square root of 10 million is close to 3000. So 3000 is not same as 10 million. You see, things are getting different. That means you will prefer an algorithm that will take less lower time complexity, which is the number of times you do the worst case divisions. 3000 divisions is not same as 10 million divisions. So when you want to decide which algorithm to pick, you will pick the second one that requires square root of n divisions compared to n divisions. And then this is the one that will go ahead and implement, not this one. So this is how you decide. So this is like a complete package. Given a problem, come up with this logic, write the pseudocode, and analyze the time complexity of that algorithm. And if there are more than one algorithms to solve that problem, write down all of them and analyze the time complexity, and then pick the one that requires the smallest or lowest time complexity, and then go ahead and implement that algorithm. Okay. Let me stop for a second. So any questions so far? Save this video too.